Okay, another application of Newton's second law for rotation. In this case, we're going to analyze this contest called a caber toss, where Scottish guys grab a big pole, like a telephone pole, and flip it up into the air and get it to stand on its end. And in this case, they flip one that's 6.9 meters tall, has a mass of 89 kilograms, and it's tipped about 15 degrees over from the vertical and is starting to rotate about the end that touches the ground. We want to estimate the angular acceleration of this rod. The reason it's an estimate is the inertia of that is complicated. It's not uniform, it's not thin, but we're going to assume that it's a uniform thin rod. That way we can estimate its angular acceleration. So this is an application of Newton's second law. So when we do Newton's second law, we have to draw a free body diagram. We used to just draw them as dots because we only worried about the center of mass motion. But now, since things are rotating, we have to draw the extended body. So there we have our big pole, and we have to identify what forces act on it. So there's gravity. Gravity will act at the center of gravity. So the location of the forces is really important when we're doing rotational applications of Newton's second law, because we have to know where that is, because we need to know the torque it produces, and torque depends on the distance from the axis. Another force, it's touching the ground. The ground exerts a normal force perpendicular to the ground, so that's going to be directed upward. Remember, normal force is perpendicular to the surface providing it. Since it's the ground providing the normal force, it will be perpendicular to the ground. It is not perpendicular to the rod. Then there's another force that a lot of people miss, and that's friction. There's going to be friction to the left, and static friction at first at this instant. And that's because the center of mass is moving left. There has to be something pushing it left, and there's that force there. Also, the bottom of it doesn't slide over, so there's clearly a force there to the left. Now when we go to apply Newton's second law for rotation, it's the sum of the torques that add up to equal the product of the rotational inertia and the rotational acceleration. So analogous to F net equal ma, but now we have F net torque equal I alpha. Now to determine torques, we have to know the axis. So what is the axis that it's rotating around? It rotates around the end that touches the ground. So our axis is right here. That's where the axis is. Very important that you identify where the axis is on these problems, because we need to know that in order to calculate the torque. Now there's three forces, all of which could provide a torque. So let's look at them. There's the torque from gravity. There'll be a torque from the normal force. There'll be a torque from the friction. Now I just put summations. I didn't even consider direction, but direction is very important. I just added them up right now, and we'll see what happens with these. So the torque from gravity, that's R for the gravity, that's the force of gravity, and that is the sine of theta for the gravity. That sine of that angle is the angle between R and F. Then likewise we have the same thing for the normal force. R to the normal force, Fn the normal force, the sine between those two things, and likewise for the friction, the distance to the frictional force, the size of the frictional force. It's static, it's not sliding. And the sine of the angle between those two things, and that's going to equal I alpha. Now we're considering I to be the object to be a thin rod, and a thin rod about its center, nope, about its end rather, about its end, its inertia is 1/3 its mass times its entire length squared multiplied. Then that's the inertia, then we multiply that by alpha. Okay, so when we look at these, for this one, the distance to the gravitational force, that's half the length, because the center of gravity of a uniform pole is at its center. It's not actually uniform, but we're going to assume it is. And again, that's why we get an estimate. So that's currently L over 2. And the force of gravity is mg. And then the angle it makes, this angle here we're told is 15 degrees. I'm just going to label that as theta. That angle will be equal to this angle. It's the same angle, opposite interior angles or something like that. No. And so that's going to be the sine of that angle theta. Then the normal force, the distance to the normal force from the axis is 0. The normal force is on the axis. Its line of action passes right through the axis. It has no distance to that. So that's going to be 0. This whole thing ends up being 0 because r is 0. So that's 0. And why is that 0? Because r to the normal force equals 0. And the friction force, its line of action passes through the point of contact. It also has a 0 moment arm. So its torque is 0. And they're going to multiply out to be 1/3 ml squared, the inertia of the rod about a 10, times the angular acceleration. So again, that's frictional torque is 0 because the distance to the frictional force from the axis is 0. All right, looks like we've got some pretty simple stuff here. And I got some space. We'll do one more line. Here we got L mg sine theta over 2 is going to equal ml squared over 3 alpha. And we kind of lost a little bit there. Here we go. Get you back in view. And if we take this over to this side, we solve for alpha, we can see that the m actually doesn't matter. And this L, that L, there's 2 of these because it's squared. There's one of those, it reduces. So we're going to end up with 3g sine theta is going to equal 2 over L. Oh, not equal. Divided by 2 over L is equal to alpha. So 3g sine theta divided by 2L equals the angular acceleration. Now, we can plug this into either one and find the answer to the second one, but we'll see as the angle gets further from vertical and more horizontal, this angle gets larger, that angle gets larger, this sine becomes larger. Right? So it accelerates at an increasing rate. At 15 degrees, some acceleration, but not a ton. At 30, it's going to have more acceleration. And then the maximum acceleration will occur when it's at 90 degrees from the vertical all the way here, right before it hits the ground. All right, this problem is useful here for this one, which is in the homework, and also another problem that's in the homework that has a horizontal rod. Hope that was helpful.